Hi dear students, today we will discuss about rare earth doped fiber amplifiers. And here we will mainly discuss about EDFA, that is Erbium doped fiber amplifier. First of all, let us see. In the case of optical long-haul data transmission systems, today we are usually operate in the C band. That is, its wavelength is ranging from 1530 nanometer to 1570 nanometer. And the standard amplifier for these systems is the Erbium doped fiber amplifier or EDFA, and this provides more gain and for high data rate links, dense wavelength division multiplexing systems with increasing bit rates per channel and decreasing channel spacings are used. Also, there is another amplifier, that is thulium doped fiber amplifier, that is TDFA, and which is used in the S band. S band is very closer to the C band. Here we will discuss about EDFA, that is Erbium doped fiber amplifier. First of all, let us see the construction of Erbium doped fiber amplifier. So, see, figure shows the Erbium doped fiber amplifier. That means if a fiber section will be doped with erbium. That is Erbium doped fiber amplifier. You can see here, this is the fiber, and this portion of the fiber will be acting as an amplifier. For that, we are doping this fiber with the erbium. So let us see its construction. Usually EDFA consists of a 10 to 30 meter length of silica fiber and whose core is lightly doped with ionized atoms of rare earth elements such as erbium. Sometimes it may be doped with white erbium, thulium or praseodymium. Here the host fiber material is usually silica or fluoride glass or telluride glass. In the case of erbium doped case, we will use silica glass as the host material and we will dope it with erbium. So the operating region of this type of amplifier is decided by the host material and also the doping element. Usually for long haul telecommunication applications, silica fiber is doped with erbium and it is the most popular choice. And here we know that in the case of an amplifier, there is a pump energy is needed, and here the fiber is pumped using a pump signal from the laser. Typically, the wavelength range of this laser is from 980 nanometer or 1480 nanometer. Here you can see that the pump laser, actually this portion acts as the amplifier. Here there is a pump laser that is seen, and here to combine the output of the pump laser with the input signal, the doped fiber is using a wavelength selective coupler. You can see here that actually it is not shown here. Here we will use, in order to couple the signal and the pumping signal, this will be provided externally by a laser, and here we are using a coupler, that is wavelength coupler. That is what we are using here. Sometimes there may be, instead of using one pump, we are using one or more pumps in order to provide higher gains. Also there will be isolators. Here you can see there is an isolator in the input side and also in the output side there are two isolators. Usually the optical isolator is used at the input and output. Sometimes it may be used at the input alone, or so we can say that the isolator may be used at the input and output, or it may be used at the input or output for any amplifier that is used to prevent the back reflections. So isolator's main function is to prevent the back reflections. So here you can see that there is a pump filter and it is used to provide linear gain. Pump filters are used to provide linear gain. Let us see the basic principle of operation of this erbium doped fiber amplifier. So you can see here that in order to know the working principle, we should need the energy levels of erbium ion in silica glass. You can see this is an energy band diagram, And here there are 3 energy bands. You can see here that first is represented by E1, next is E2, third is E3. So you can see here that E1 is the ground state band, E2 is the metastable band, and E3 is the pump band. And you can also see there are different lines that are representing the upward transition and downward transition. You can see here that this is the upward transition. So here from an excited atom from the E1 ground state band will be excited to the E3 pump band with the help of the pump energy, which is of 980 nanometer wavelength. So this 980 nanometer will be provided by the laser pump. See, you can see here that there is a pumping laser which will provide the wavelength 980 nanometer here, and the electrons will be absorbing. Electrons in the ground state will be absorbing this energy of 980 nanometer, and they will be excited to the higher energy state, that is E3 pump band. And this E3 pump band has an energy gap of corresponding to 1.27 electron volt from this ground band. So these electrons will reach here. Also you can see there is another upward transition, and this upward transition is taken from the E1 band to the E2 band, and in order to transfer the electrons in this E1 band to this E2 band, the electrons or atoms will be absorbing an energy corresponding to 1480 nanometer. Usually some pump lasers provides a pumping energy that is corresponding to a bandwidth of 1480 nanometer. So that band of energy will be absorbed, that energy corresponding to this wavelength will be absorbed by the electrons in the ground state, so that they will be jump into the E2 metastable band. That is, here you can see that there is a transition from the E1 ground level to the upper side of this E2 metastable band. You can see here that there is an E1 in the E2, there are 2 lines. One represents corresponding to the upper side and other corresponding to the lower side, and so the energy difference or energy band gap between this ground state band and the upper layer of this E2 band is 0.841 electron volt. Similarly, the energy band or energy gap between this E1 ground state and the lower side of this E2 metastable state is 0.814 electron volt. So when an energy corresponding to the wavelength 1480 nanometer pump is absorbed by the electrons in the E1 ground state, they will be jump into the E2 metastable upper side of the E2 metastable band, and finally there will be a population inversion takes place in this E2 metastable band. Sometimes the electrons in this upper level maybe go to the lower side of this E2 metastable band. As a result, there will there is a formation of the population inversion between this E2 metastable band and E1 ground state. When the population inversion achieved, if you are providing again the pump energy, so that the electrons in this metastable state will be stimulated, will undergo stimulated emission, so that they will be going to this going from this metastable state to this ground state band, so that they will emit photons of energy. Sometimes if there is no pump is provided, when population inversion is achieved, sometimes there is a chance of spontaneous emission, that is shown here. Due to this spontaneous emission, some photons will be generated, and these photons will not be in the frequency range corresponding to this pump energy. As a result, the photons emitted due to this spontaneous emission will produce some noise in this Erbium doped fiber amplifier. This corresponding to the amplified spontaneous emission noise. That means there will be some output without any pump signal, or without any input. There will be some output at the amplifier section, that corresponding to the amplified spontaneous emission noise. Similarly, you can see here that from the E3 band, see here some electrons are excited to this E3 band. When they are absorbing an energy from the pump energy corresponding to the 980 nanometer. That electrons may be radiating, that electrons may be, this higher energy level is not a stable state, so those electrons may be going to this metastable state in order to achieve stability. So this corresponds to non-radiative decay. That means no photons will be emitted in this process. Actually here the population inversion takes place between the E2 metastable band and E1 ground state band when suitable pump energy is obtained. For this obtained suitable pump energy is given to this state, the electrons in this metastable state will be going to the lower energy state, that is E1 ground state. As a result, stimulated emission takes place, and this gives rise to more photons. So this is corresponding to the amplification of the input signals. So this is the working, and here you can explain it as E3 is the pump band with energy difference of 1.27 electron volt from the ground level, and this energy corresponds to the wavelength of 980 nanometer. Similarly, there is E2 metastable state, and the top of this band has an energy difference of 0.841 electron volt from the ground level, that is correspond to the wavelength of 1480 nanometer. And the bottom of the metastable band has an energy difference of 0.814 electron volt from ground level, that is corresponding to a wavelength of 1530 nanometer. See, here there is the emission of photons due to the decay of electrons from this metastable state to ground state. So this photon energy is corresponding to the wavelength of 1550 or 1530 nanometer. E1 is the ground state band, and here upward arrow indicates the wavelength at which the amplifier can be pumped to excite the ions into the higher energy level, and the downward transition represents the wavelength of photons emitted due to the spontaneous and stimulated emission. Here the pump laser emitting photons of wavelength 980 nanometer is used to excite the ions from the ground state to the pump level, and these excited ions decay very quickly from the pump band to the metastable band. During this decay, the excess energy is released as mechanical vibrations in the fiber. In the metastable state, the electrons of excited ions tend to populate at the lower end of the band. Another wavelength, that is 1480 nanometer, can also be used for the pumping, and the absorption of this wavelength, that is corresponding to 1480 nanometer pump, photon excites an electron from E1 to the top of E2, and some of these ions can decay back to the ground level in the absence of external stimulating photon flux, and this phenomena is known as spontaneous emission, and this causes amplifier noise, and that amplifier noise is known as amplified spontaneous emission noise. And in the stimulated emission process, the signal photons triggers an excited ion to drop to the ground state, thereby emitting a new photon having the same energy and polarization as the incoming signal photon. That is the important thing. That is, in the stimulated emission process, the signal photon triggers an excited ions in the metastable state E2, and it will be dropped into the ground state corresponding to E1, so that it will emit a photon having the same energy and polarization as the incoming signal photon. In a two energy level atomic system, only an optical signal at the frequency Fc satisfying HFC equal to E2 minus E1 is amplified. So in the case of Erbium doped fiber amplifier, instead of using the energy levels, we are considering it as a energy band. That means if these levels are spread into bands, all the frequencies corresponding to the energy difference between some energy in the E2 band and some energy in the E1 band can be amplified. This the process of amplification takes place in the erbium doped fiber amplifier. So next, in the EDFA, the set of frequencies that can be amplified by stimulated emission from E2 band to the E1 band, that is corresponding to the wavelength range of 1525 nanometer to 1570 nanometer. That means it provides a bandwidth of 50 nanometer. Next, we will see the advantages of this EDFA. The EDFAs have high power transfer efficiencies from the pump laser from the pump to the signal, that is approximately greater than 50%, and it has got a wide spectral band amplifications with a relative flat gain, and that gain is greater than 20 dB, and this gain is so that EDFs are useful for WDM, that is wavelength division multiplexing applications, and it will give a saturated output that has a power of greater than 1 milliwatt, and long gain time constant is acquired in this case, that is greater than 100 millisecond, and large dynamic range of operations will be there, and also it has got a low noise figure. The output is polarization independent and suitable. It is suitable for this type of amplifiers, are suitable for long haul applications. So it has got some disadvantages, such as it has got a relatively large, these are relatively large devices, that means an optical fiber cable of length 10 to 30 meter is used, is necessary for implementing a EDFA amplifier, and such devices are not easily integrated with other devices, and also there will be a presence of amplified spontaneous emission noise, ASE, and also there will be chances of crosstalk, and gains also there is gain saturation effects. These are the drawbacks of EDFA. Next we will see different configurations of EDFA. Basically there are three possible configurations of EDFA, that is co-directional pumping. See, this is the case of co-directional pumping configuration. Next is counter directional pumping, and this is figure corresponding to the counter directional pumping, and next is dual pumping. See, first one is co-directional pumping. Before that, the complete setup basically consists of fiber amplifier. You can see this is the fiber amplifier. It is doped with the erbium, so that it represents an amplifier section. This is the length of the fiber which is used to implement the fiber amplifier, and the other sets are sometimes it may use one or more pump lasers, and here we are using only one pump, and in this case we are using two pumps. Here this represents one pump, and here this represents the other pump. Actually it is a dual pumping configuration, and this is a single pumping configuration, and the pump is in the co-direction. It is co-directional pumping structure, and also in this structure there are passive wavelength couplers are used. So you can see that there is also tap, or there is also optical isolators which is used to prevent the back reflections, and also there is a dichroic coupler, and this dichroic couplers couples the pump here. This is the wavelength selective coupler. It acts as a dichroic coupler, and which is used to couple the pump, and here this is the pump laser, pump and signals to this fiber. That is with this help of wavelength selective coupler, the signal, that is input signal and pump energy is coupled to this erbium doped fiber amplifier, and here you can see that the pump energy is provided in the same direction as that of the input. That is why it is called co-directional pumping. Also you can see that there is another tap couplers. You can see here there is a tap coupler. Instead of this dichroic coupler, there is also another tap coupler at the input and output, and which is used at the input and output sides, which is used for monitoring the input and output. And next case is the counter directional pumping. Here this configuration uses the same structure as that. It is it using the erbium doped fiber amplifier, dichroic coupler in order to used to couple the input and the pump signal, and also isolator at the input and output side in order to prevent the back reflections, and also input and output are monitored by using devices, and it uses tap couplers. See, here one difference is that here you can see that the pump signal is provided opposite or counter direction to that of the input signal. Here input is providing in this way, but the pump laser is provided in the counter direction as that of the input. Next case is that this configuration uses dual pumping. You can see at the input side and output side there are pumping sources are used, and In this case, other structure is similar, other types of components used are the similar. Here there is an erbium doped fiber amplifier and isolators, and also tap couplers used to monitor the input and output. And this structure or this configuration is used to provide high gain or high linear gain. And this is about the different configurations of EDFA. So this is a working explanation, that is 3 possible configurations: co-directional pumping, counter-directional pumping, and dual pumping. And the complete setup of the doped optical fiber amplifier consists of doped fiber, one or more pump lasers, and a passive wavelength coupler, and optical isolator, and a tap coupler at the input and output sides to monitor the input and output. And also there is a dichroic coupler, which is wavelength selective coupler, which is used to pump, which is used for coupling the pump and signal power into the optical fiber. And also optical isolators prevents the amplified signal from reflecting back into the device. And co-directional pumping, here pump light is injected from the same direction as the signal flow. In counter-directional pumping, the pump power is injected in the opposite direction to the signal flow. This provides high gain and better noise performance. And in the case of dual pumping, an additional pump laser can be used at each end of the fiber, and one pump beam propagates in the signal beam and the other propagates against to the signal beam, and this ensures the population inversion and gain remains constant along the fiber. Next we will see the gain of the EDFA. And here you can see that the different factors are controlling the gain of the EDFA. First one is the concentration of the erbium ion, and next is optical gain flattening filter. By using this, we can control the gain of the EDFA. Also sometimes we are providing additional pumping laser to provide linear gain regions. And this is the gain band of EDFA diagram. You can see actually this dotted line represents the unflattened EDFA gain. Sorry, this darker line shows the unflattened EDFA gain, and this dotted line represents the gain flattened EDFA line. And you can see here that if you are going to the analysis side, you can see the input and output powers of EDFA can be expressed in terms of the principle of energy conversion, that is P signal out less than or equal to P signal in plus lambda P divided by lambda S into P pump in, where P pump in is the input pump power and lambda P and lambda S are the pump and signal wavelength corresponding to the pump and wavelength corresponding to the signal. And so we can rewrite the equation as gain will be equal to P signal out divided by P signal in. That means we are dividing it with the P signal in, so that we will get gain. Gain will be equal to P signal out by P signal in. That will be less than or equal to 1 plus lambda P pump in divided by lambda S P signal in. And in this case, by rearranging the equation, we will get a P signal in will be equal to lambda P by lambda S into P pump input divided by G minus 1, where G is the gain. And the maximum output signal power depends upon the ratio lambda P by lambda S. So we can find the power conversion efficiency of the EDFA as a power conversion efficiency PCE equal to P signal out minus P signal in divided by pump in. So that's all about this EDFA topic. Thank you. And this is the gain band curve of the EDFA. You can see that there is a higher gain at this point, that is corresponding to 1535 nanometer, and at the other region it provides linear gain, but that is above the this 1535 nanometer wavelength range. So that's all about this EDFA. Thank you.